This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to this discussion on a paper focusing on recurrent neural network, RNN, regularization. The authors introduce a novel technique for applying dropout to long short-term memory LSTM networks, significantly improving their performance. Let's start with the core problem. Why is regularizing RNNs, specifically LSTMs, challenging? Traditional dropout, highly effective in feed-forward networks, doesn't directly translate to RNNs. The recurrent nature of RNNs means that noise introduced by dropout gets amplified over time, hindering learning and potentially disrupting the network's ability to capture long-term dependencies. This is particularly problematic for LSTMs, which are designed to handle these dependencies. So the paper proposes a solution to this amplification problem. Can you describe their approach to applying dropout within LSTMs?
Their key innovation is to apply dropout selectively. Instead of applying dropout to the recurrent connections, the connections that maintain the network's memory across time steps, they apply it only to the non-recurrent connections. This preserves the LSTM's ability to maintain long-term information while still introducing the beneficial regularization effects of dropout.
That's a subtle but crucial distinction. Can you elaborate on why applying dropout to non-recurrent connections is more effective?
By leaving the recurrent connections untouched, the LSTM retains its capacity for remembering past information. The dropout on the non-recurrent connections introduces noise that forces the network to learn more robust representations, preventing overfitting without compromising its ability to handle long-term dependencies. The noise is not amplified through the recurrent connections.
The paper demonstrates this approach across several tasks. Let's discuss the language modeling results on the PenTreeBank dataset. What were the key findings there?
They trained both medium and large LSTMs with and without their proposed dropout regularization. The regularized models consistently outperformed the non-regularized ones, achieving significantly lower perplexity scores, a measure of how well the model predicts the next word in a sequence. The improvement was particularly dramatic for the larger LSTM, where overfitting was a more significant concern.
And what about the other applications? How did the proposed method perform in speech recognition and machine translation?
In speech recognition, using the Icelandic speech dataset, the regularized LSTM showed improved frame accuracy, a metric closely related to word error rate. In machine translation, using the WMT14 English to French dataset, the regularized LSTM achieved a higher BLEU score, a metric for evaluating machine translation quality, indicating better translation performance. Similar improvements were observed in image caption generation.
The paper mentions some related work. Were there any other approaches to RNN regularization that the authors compared their method against? What were the key differences?
Yes, they discussed other work, including marginalized dropout, which is a deterministic approximation of standard dropout. However, their approach of selectively applying dropout to non-recurrent connections is distinct and appears more effective. They also cite independent work by Pagilal, 2013, that arrived at a similar method applied to handwriting recognition. The authors also discuss the architecture of the LSTM they used. Were there any specific architectural choices that were particularly important for the success of their regularization technique? The paper details a deep LSTM architecture with multiple layers. The specific architecture is described by equations detailing the input, forget, output, and cell state updates. The key is that the dropout is applied before the affine transformations that combine the inputs to these gates, ensuring that the noise doesn't propagate through the recurrent connections.
Given the success across multiple domains, what are the broader implications of this work for the field of RNNs and deep learning in general?
This work significantly expands the applicability of dropout to RNNs, a previously challenging area. It provides a practical and effective regularization technique that can be readily applied to various RNN architectures and tasks, potentially leading to improved performance and larger, more powerful models. The selective application of dropout is a key contribution.
Were there any limitations or potential areas for future research highlighted in the paper?
While the results are impressive, the paper focuses on a specific LSTM architecture. Future research could explore the generalizability of this selective dropout approach to other RNN architectures and variations of LSTMs. Further investigation into optimal dropout rates for different tasks and network sizes would also be beneficial.
The paper mentions computational resources used for training. Can you comment on the computational cost of training these models, both with and without the proposed regularization?
Training the larger models, especially the large regularized LSTM, was computationally intensive, requiring a full day on an NVIDIA K20 GPU. The non-regularized models required less training time, but their performance was significantly lower. This highlights the trade-off between computational cost and improved performance through regularization.
The paper provides perplexity scores and BLEU scores as evaluation metrics. Are there any other relevant metrics that could be used to assess the performance of these models, particularly in the context of the different tasks?
Yes, depending on the specific task, other metrics could be relevant. For speech recognition, word error rate, WER, is a standard metric. For machine translation, other metrics beyond BLEU, such as Meteor or Rouge, could provide a more comprehensive evaluation. In image caption generation, metrics like CIDR could be considered.
The authors mention the importance of initializing the hidden states. Can you elaborate on the significance of this initialization and how it might affect the performance of the model?
The initialization of hidden states can significantly impact the performance of RNNs, especially during early training stages. The author's choice to initialize to 0 and then use the final hidden states of one mini-batch as the initial state of the next is a common practice that helps to maintain a degree of continuity across many batches. Different initialization strategies could be explored.
The paper mentions gradient clipping. What is the purpose of gradient clipping in training RNNs, and why is it particularly important in this context?
Gradient clipping is a technique used to prevent exploding gradients, a common problem in training RNNs, especially deep ones. Exploding gradients can lead to instability and hinder learning. By clipping the gradients to a maximum norm, the training process becomes more stable and allows for the use of larger learning rates.
The authors use a specific learning rate schedule. Can you explain the rationale behind their choice of starting with a high learning rate and then gradually decreasing it?
Starting with a high learning rate allows for faster initial progress in the optimization landscape. Gradually decreasing the learning rate helps to fine-tune the model and avoid overshooting the optimal solution. This is a common strategy in training deep learning models.
The paper mentions the use of mini-batches. What is the advantage of using mini-batches instead of processing the entire data set at once?
Using mini batches reduces the computational cost of each training iteration, making it feasible to train large models. It also introduces stochasticity into the training process, which can help to avoid getting stuck in local optima.
The paper highlights the importance of the number of training epochs. How was the optimal number of epochs determined for each model?
The optimal number of epochs was likely determined through experimentation and monitoring the validation performance. Training was stopped when the validation performance started to plateau or decrease, indicating overfitting.
The paper mentions the use of different initialization ranges for the weights of the medium and large LSTMs. What is the rationale behind these different ranges?
The choice of weight initialization range is often task-specific and can influence the training dynamics. The authors likely experimented with different ranges to find what worked best for each model size. Smaller ranges might be preferred for larger models to prevent initial weights from being too large.
The paper provides code availability. How valuable is this for reproducibility and further research in this area?
Providing code is crucial for reproducibility and allows other researchers to build upon the work. It facilitates verification of results and enables further experimentation and extension of the proposed method.
Looking back at the overall findings, what is the most significant contribution of this paper to the field of recurrent neural networks?
The most significant contribution is the demonstration that a carefully designed application of dropout can be highly effective in regularizing LSTMs, leading to substantial performance improvements across various tasks. This addresses a long-standing challenge in training large RNNs and opens up possibilities for building more powerful and robust models.
This has been a thorough discussion of the paper's key contributions and implications. Thank you.